Okay. Apologies everyone for the delay. We had some technical difficulties, but that's been solved right now. Oh yeah, you have to. So our speaker today is Dr. Gade Pedersen. Sorry. And she's from the University of Sydney. And she's going to talk to us about asteroseismology today. Sorry.
Hi everyone, thank you for having me and sorry about the wait. I will also make one quick disclaimer or a word of warning. I did try to update my laptop last week. So now it likes to freeze at some point. So let's keep fingers crossed it's well behaved throughout the seminar. So again, thank you for having me. My talk today, as you might have realized already, is an asteroseismology, but more specifically asteroseismology of massive stars. And hopefully by the end of the day, I'll have managed to convince you all that asteroseismology is super cool, and it's a very useful tool that we can use for studying the interiors of stars. So just general perspective. So I'm sure you're all familiar with these kinds of diagrams. So if you're looking at stellar evolution in general, stars will evolve in two different ways depending on their initial mass. And again, the stars that I'm super interested in and are going to be the focus of this talk are the massive stars. And why that? Well, we also refer to them as the chemical factories of the universe. And that's because during their lives and through their deaths, they're responsible for producing the majority of elements that are heavier than hydrogen and helium. So if you want to understand chemical evolution, massive stars are super important for this. Now, if we look at what the interior structure of these stars look like, you see here on the left a 3D model of such a massive star. We tend to divide these models into there we go. Yeah. Into three different regions. Okay. Where we have one region is the convective core. So unlike the sun, which has a radiative core, these types of stars have convective cores. Outside of that, we have a radiative envelope. And then in between the two, we have a transition region between the two. And so through the main sequence evolution of these stars, the process that's dominating the nuclear burning is the CNO cycle, where we have isotopes of carbon, nitrogen, and oxygen that acts as catalysts throughout the nuclear burning. And in doing so, ends up producing a helium from hydrogen. Out of these reactions, the slowest one is where we're transforming nitrogen into oxygen. And because it's a slow reaction, that means we end up building up nitrogen in the cores of these stars. And then if we have mixing that's taking place in the envelopes of these stars, that means we can transport excess nitrogen from the core to the surface and thereby modify the surface abundances that we see for the stars. But also, in my case, most importantly, you can renew the fuel that's available for the nuclear burning during the main sequence of these stars. And again, these stars have convective cores. And what that means is that the mixing is very efficient. The element transport happens on dynamical timescales. So efficiently, all the material or hydrogen that enters the core is available for nuclear burning. And so by adding in extra hydrogen from mixing, we can effectively extend the main sequence lifetimes. And we also end up with much bigger helium cores than we would otherwise predict for these types of stars. Now, the mixing inside stars, we can describe using these types of mixing diagrams, as they call them, where you have the logarithm of the mixing efficiency on the y-axis. And on the x-axis, we have the mass coordinates inside the star going from the center towards the surface. And just like with the interior structure, we also divide these diagrams into three different regions, where we have in gray is the convective core, where you see the mixing efficiency is very high. So just discuss why that is the case. Then we have mixing in the envelope, which is shown in green, And in between the two, we have what we call convective boundary mixing. So that's the extra mixing that is taking place in this transition region that you're seeing. Now, the issue that we have is we don't actually know what these mixing profiles look like, okay? And how much mixing is taking place outside of the convective cores of these stars. So because this is an unknown and an uncertainty, then that's one of our major uncertainties in the stellar structure and evolution of massive stars. So just to illustrate what the effect of this mixing is, just looking at the effect of this convective boundary mixing, so this blue region that you're seeing, and what happens if we increase the size of this region, okay? So in the middle, you see the evolutionary tracks for a main sequence star going from white to dark blue, which corresponds to increasing the size of this convective boundary mixing region. And on the right, you see correspondingly what the hydrogen mass fraction profile looks like. Okay, so that's for the inner 35% of the star. That's showing you how much hydrogen is left at a given mass coordinate. And what you see here is that effectively this extra mixing is increasing the size of our cores as well. So if we try to put these in approximate numbers, if we compare scenarios of having minimum convective boundary mixing to a large amount, then effectively you can increase the age or the time the star spends on the main sequence by about 40%. And the helium cores we end up with at the end of the main sequence evolution, you can double in size compared to what's otherwise predicted. So the issue is we don't know what these mixing profiles look like. And also when we study stars, all that we're really observing is their surface properties. And so how are we ever going to be able to understand the interiors of these stars? So that's a question that was raised by Sir Arthur Stanley Eddington about 100 years ago. He was asking what kind of appliance can we use to really look deep into the stars and understand what's happening in their interiors. So Eddington believed we would never be able to do this. He thought the way of moving forward is using theory. We know our theory well, therefore we can compute what an internal structure is like, and then we can try and compare the positions of the stars in the HI diagram and see how well that matches to the theory. As it turns out today, we can do much better. And the inspiration that we've taken is essentially from seismologists studying earthquakes. So using that analogy, what happens when we have an earthquake occurring on the Earth, it sends waves that propagate throughout the interior of the Earth. And when it's hitting regions of different densities, those waves will bend and arrive at the surface at different positions that we would otherwise predict. So the way that seismologists, let's say, go about studying waves in planets is by placing seismometers around the Earth and then measuring also arrival times of these waves and whether these waves are seen or not. So some waves cannot penetrate different parts of the Earth, and that's why we get these shadow regions. In a similar sense, as it turns out, stars also have waves in their interiors. They're fundamentally very different from the waves that we see in the Earth. But you see here a simulation of such types of waves.
I'm trying to get it into my earpod, but...
Hi, Jenny.
Hey, sorry.
It's all good. So you have again here the convective core that's generating waves that you see as temperature fluctuations here that are propagating throughout the star. And you see temperature fluctuations at the surface, which corresponds to a variation in surface brightness of the star. Okay. Then when we're studying waves in planets, we're using seismology. And if we're studying waves in stars, we're using asteroseismology instead. And so asteroseismology has two main goals. On one hand, we want to be able to provide precise stellar parameters, such as masses, ages, and radii, and so forth. And the other goal of asteroseismology is to provide good constraints on the interior properties of the stars, such as the mixing profiles and the rotation rates. And if you read my abstract, you might have guessed that this second point is exactly the focus of this talk. And so as it happens, the good news for us is that pulsating stars are found all across the HR diagram. And I really want you to show this special kind of HR diagram, what happens to be my favorite one. And why is that the case? So this HR diagram, the asteroseismic one, will tell me, it's a great one, huh? Will tell you if at any point during the evolution of the star, it passes through any one of these shaded regions, then we expect the star to pulsate. And if it's pulsating, then we can learn something about the interior properties of the stars by studying these pulsations. Now, how do we do that in practice? How are we studying these pulsations? Well, as I mentioned, the pulsations are observed as changes in the surface brightness of the star as a function of time. And when we are studying pulsations, what's really important is that we're able to observe these stars for a long time. So I'm trying to illustrate it here. What you have here on top is an actual observed light curve of a B-type star that's pulsating. Each one of these measurements is a measurement of the variation in brightness of the star as a function of time. And on the bottom panels, you see the Fourier transform of this light curve, assuming 3 different lengths. And so what you see here is, on one hand, the resolution of our Fourier spectrum increases as we're increasing the length of the time series, which means that not only can we observe more oscillations in the stars, but also the precision by which we can do that also increases. And the more precise we can measure the oscillations, the better constraints they can give us on the interior structure of the stars. So if you're looking at the best kind of data we have available right now for studying pulsation in stars, those come from the Kepler Space Telescope, which observed the same patch of the sky continuously for 4 years. And so every half hour, it would deliver a measurement of the brightness of the star, and did so continuously for 4 years. That's really the best data we have available for doing astroseismic studies right now. The bad news for me is that the most massive stars observed by Kepler are the B-type stars. So because of the choice of the field of view, Kepler did not actually measure or observe any of the stars we would call supernova progenitors, so the very, very massive stars. And that's just because if you're interested in looking for exoplanets, which is what Kepler was the main focus of Kepler, then bright stars are really annoying. And that's the massive stars. Yeah? So unfortunately, we can't go up to the very high mass stars with Kepler, but we can go to the B-type stars, or more specifically, these slowly pulsating B-type stars that are found right here in the middle of the asteroseismic HR diagram. So these type of stars oscillate in gravity modes, where we have gravity is acting as the restoring force. So when we are perturbing the structure of the star from these oscillations, what's bringing them back to equilibrium is gravity, or buoyancy. And now, before going into why these gravity modes are great, just want to give you a very quick crash course on asteroseismology and how we astroseismologists like to characterize stellar pulsations. And we do so using 3 different quantum numbers that is associated with the number of nodes that an oscillation has. Okay, so there are 2 types of nodes on the surface, which you see at the left half up here. So those are the white lines that are nodes that cross the total number of nodes on the surface. So that's a degree L, and M is the number of nodes across the equator. Okay. On top of that, we have the interior nodes. So that's the radial order of the oscillations. That's just the number of nodes, radial nodes that we have inside of the star associated with the given oscillations. Now, I want you to know this because gravity modes have a certain property, and that is that they're roughly equally spaced in period and form what we call period spacing pattern. So these 2 equations you see here are essentially how we can calculate what the periods of the oscillations are. And they depend on the degree, L, the radial order N, and this pi naught value, which is essentially an integral of the Brunt-Väisälä frequency. So the Brunt-Väisälä frequency is the oscillation frequency you get of a blob of gas that you're displacing in the radiative envelope of the star. And so as it happens, if you're looking at oscillations that have the same L and M value, so these, like these ones, but are consecutive in N, and we calculate what's the period difference between these P2 and P1, and P3 and P2, then it turns out that these periods are roughly the same, these differences. And so what we do with these kind of period differences, if we take them and plot them as a function of period, we get kind of what we call period spacing patterns. And to make it easier for ourselves to see if there are any deviations from this, we connect all these dots by a line. Okay, so then it's relatively easy to see if there are any deviations. Now you might have noticed that I'm mentioning here, this is the case if you have a non-rotating star that's chemically homogeneous, then we have these kind of straight patterns. So what happens as soon as we introduce rotation? So when you have rotation in the star, we're getting rid of one degeneracy associated with the frequencies, meaning that we end up splitting up the frequencies in a number of oscillations, so a number of peaks in our Fourier spectrum corresponding to 2L plus 1. Okay, so but the important part here is that essentially, if we are looking at what happens to the patterns, then modes that are traveling in the direction of the rotation, as you see here on the right, where you have this axis here that I'm showing is the rotation axis. Modes that are traveling in the direction of the rotation will take less time to go around the star compared to modes that would be traveling in the opposite side opposite direction of the rotation. So effectively, if we're just looking at this example over here, with modes traveling in the direction of the rotation, you're increasing the frequency that corresponds to decreasing the period. And in the end, that gives you a tilt in your period spacing patterns. And by measuring that, we can get a measurement of the interior rotation of the star. So that's the effect of the rotation. On top of that, we have effects of chemical gradients inside the star. So now again, on the left, you have the hydrogen mass fraction profile. So how much of the mass comes from hydrogen inside the star as a function of the inner 35% of the star. So the blue is our zero age main sequence. The green is towards the TAMS, the terminal age main sequence, where we have a hydrogen depletion in the cores of the stars. We used all the hydrogen for the nuclear burning. And on the right, you see the corresponding effects of the period spacing patterns of having the star evolve and become older. So what's essentially happening here, as the convective core is shrinking during the main sequence evolution of the stars, it leaves behind this chemical gradient, and this chemical gradient acts to trap the oscillations, and it gives rise to this kind of zigzag pattern morphology in the pattern. Okay, so that's why we can use the morphology of the patterns to not only measure ages, but if you have mixing, that's going to change your chemical gradient and thereby also the morphology. So in summary, if you're looking at examples here of observed period spacing patterns for 7 stars, SPB stars that were observed by Kepler, then in summary, the slope of the pattern tells you how fast the star is rotating. The average level, average value of the pattern tells you something about the mass and age of the star, whereas the morphology is related to the age and the mixing of the stars themselves. So prior to my studies, there's actually only a few examples of cases where people have tried to model these period spacing patterns of the star. And I'm showing you here the position of these stars in the age-like diagram, where the shaded region here corresponds to the instability strip of the SPB stars. So the brighter yellow in color, the more oscillations we expect to be excited inside the star. And as you can see here, prior to the studies that I did, only very few of these kinds of patterns had been modeled. And what we were able to do is to increase the sample to 26 SPB stars and try to really get good constraints of what the interior mixing of these types of stars look like. We did this using a different set of observations. So the period spacing patterns we get from Kepler, we have spectroscopic parameters from spectroscopy ground-based observations, and combined with Gaia distances, we also have a luminosity. So these kind of parameters we use in different ways. So the spectroscopic parameters and luminosities we're using to limit the models that we're going to consider for each star, because we have some information already of where the star should be in the HR diagram. And then on top of that, what we're actually directly comparing to the models are these period spacing patterns. So the way this is done, the way that we can define a stellar model is that it's a function of some fixed input physics and some physics, some parameters that we're varying. So the fixed input physics could be the shape of this internal mixing profile. And on top of that, we're varying the masses, the ages, metallicities, and how much mixing there's in the star. When we have these models calculated with the stellar evolution code META, we toss them into a stellar oscillation code that's called a gyre, from which we vary these mode identifications, these L, M, and N values, and the rotation rate of the star as well, to then obtain these period spacing patterns from theory that we compare to the observations. So I'm showing here some examples of observed period spacing patterns compared to the theoretical best matching ones that we obtained from the modeling, where the diamond points collected with the fall lines are the observations, whereas the a bit fainter patterns that you're seeing are the actual theoretical predictions that we end up getting that best match the observations. And so as you can see, we're actually getting pretty good fits to the observations here in this case. So what does this tell us about the internal mixing of these stars? Well, what we did initially was to consider 8 different versions of what the internal mixing profile looks like. So that's combining 4 different shapes of the envelope mixing with 2 different shapes of the convective boundary mixing. But in one case, we're assuming that the convective boundary mixing just effectively extends the size of the convective core, but the mixing is constant within that region. And in the other case, we're assuming that the mixing is exponentially decreasing as we're moving further away from the core. And so from modeling the S+B stars, I'm going to show you now the same diagram, but now the number of profiles you see in each subplot corresponds to the number of stars that preferred that given profile, or that's the profile that did the best at reproducing the observations. So what you can see here, there's no one single profile that does the best for all of the stars. But what you might notice is that, first of all, most of the stars are found here in the lower panels. So that's hinting towards the up stars, like the step-like function in the mixing profile to match the observations. And we're also seeing that a lot of the stars prefer having this kind of stratified envelope mixing as well. And we're also seeing that the mixing levels that we're seeing inside the stars are very diverse. So if we're looking at the parameters here that we're finding, and looking at the core masses of the stars as a function of how much envelope mixing we have. So all you need to know about this parameter is that it sets the amount of mixing we have when we go from convective boundary mixing to envelope mixing for the stars. And the color of the points that you see here corresponds to how much hydrogen is left inside the star. So that's a proxy for the age. So 1, we have all hydrogen left, no nuclear burning or not much nuclear burning has happened, and 0 means that we have the terminal age main sequence. And so what we're seeing here is that as we increase the envelope mixing of the stars, then there's a tendency that the core mass also increases as well. If we look at the relation to how fast the stars are rotating, then we also see there's a dependence on the envelope mixing on the rotation rate of the star, where the envelope mixing increases the faster the star is rotating. So that's not necessarily a surprise. We know that if we have rotational mixing inside the star, we expect the amount of mixing that we get to be higher the faster the star is rotating. But you might also see there is one outlier up here, which looks interesting, that you have a star that's rotating slowly, but is found to have a high amount of envelope mixing. And just to show, I've shown also 2 additional stars in this, which we did not include as part of our modeling, but for which also moderate levels of envelope mixing were found, although the stars are relatively slowly rotating. So that's just to say that for some stars, maybe rotational mixing is not the dominant effect that is in place here. Now that we have these models, we know the mixing levels of the stars, the current ones. We can also go ahead and predict how big the helium cores would be at the end of the main sequence evolution. And so that's essentially what we've done here, where you have the mass on the x-axis, so the mass of the star, versus the amount, how big the helium cores are on the y-axis. And here the dashed black line corresponds to the minimum amount of mixing that were included in our grid of models. And all I really want you to take away from this diagram is that as we're increasing the levels of mixing in the envelope, we do see a tendency that also the helium core masses are increasing as well. So we have some observational evidence for this too. Now I talked about mixing. Next up, I wanted to talk a bit about rotation, what we inferred from that. And so I mentioned earlier that the rotation causes as a tilt of your period spacing pattern. And actually, we don't have to do a full modeling of the star to really study what happens to the interior rotation of the stars, because we can just model or fit this slope without having to do a full model. So what I've done here is increase the sample a bit with other stars that which show gravity mode pulsations, for which we also have measurements of the interior rotation rate, but where the measurements came from a variety of different space telescopes. And the different panels here are essentially the same. They're just using 3 different age indicators. So on the left, we have the current core hydrogen mass fraction versus the initial one. The other one, the second one, is the current age of the star divided by the main sequence lifetime. And then on the right, we have the surface gravity of the star. And as you can see, independent of which age parameter that we're looking at, for a sample of SPB stars, slowly pulsating B stars shown in blue, we see a general decrease in the rotation rate of the star as they become older. This is different, or not as obviously seen, for a group of stars we have here in gray, which also happen to oscillate in gravity mode and have these period spacing patterns, but they're much less massive than these SPB stars. So these are known as Gamma Dorado stars. Here we are at masses of about 1.4 solar masses, compared to the 2 to the 3 to 10 solar masses for the SPB stars. And as you can see here, there's no such a clear trend for the Gamma Dorado stars. Now, one question we want to ask, is this something that we would normally predict to see, this decrease in rotation rate as a function of age? And so to answer that, I considered 3 different scenarios, as shown here, where the first scenario is we assume that no angular momentum transport is happening in the star. The second scenario in blue is assuming that we have a solid body rotation. And in the last scenario, we're assuming we have angular momentum transport from the Sprague-Taylor dynamo. On this diagram, I'm showing you on the top and bottom panels, the only difference is the age indicator again, so whichever one you prefer looking at. Difference between left and right is whether or not we're looking at the interior rotation and the surface rotation rate. And this interior rotation, we're measuring as kind of the average rotation that we expect these gravity modes to experience throughout the interiors of the stars. And so really what I want you to take away from this is that independently on what kind of angular momentum transport scenario that we're looking at, in all cases, we see a decrease in the rotation rate of the star as they become older. Okay, so the results we saw before does not seem too surprising, but what we can do now is to have a look at what happens if we take these rotation profiles and scale them and see which regions of these rotation age diagrams of the span for the stars that we're looking at. So we're taking these rotation profiles, we scale them to the rotation rates of the stars and then see which regions do we get in the end. So I'm showing an example of that here, where again, left and right are just the different age indicator, whichever you prefer looking at. The black points here are the average rotation rate and standard deviation for the stars in these 4 different age groups that I've marked. And what you see here, we have 2 regions that show up in these diagrams according to whether or not we're assuming solid body rotation and no angular momentum transport. And what I really want you to take away and notice from this is that we end up with regions here for the older stars, where we expect to find rotating the stars in the case of no angular momentum transport, but they're not found at all, okay? Compared to the case where we have solid body rotation. So what this is essentially telling us is that, well, we have angular momentum transport happening inside the stars, but also it's very likely that it's happening very efficiently for the stars as well. Now there's something else we can do now that we have the rotation rate of the stars, and that is we can actually measure what the inclination angles of these stars are for the oscillations with respect to how we are viewing the stars. And we can do that because we have from spectroscopy V sin I measurements. From asteroseismology, we have a rotation frequency measurement. And if we, for the stars where we've done asteroseismic modeling, we also have a measurement of the radius of the star from asteroseismology. And so here on the left, I'm showing you what the V sin I versus this equatorial velocity calculated, assuming the stars are rigidly rotating, and what these, where the stars are located in this diagram. Now, the sizes of the points corresponds to the amplitude of the dominant pulsation inside the star. And what you might notice if you're looking at this diagram is that the highest amplitude pulsations, the pulsators, tend to also be rotating slower. And that might explain that prior to our studies, looking at SBB stars observed from the ground, those were all found to be slowly rotating. But if those are more difficult to find because the amplitudes are smaller, then that could explain why we actually see them in the space data for these stars. Now, doing this, rearranging the equations a bit, we can calculate what the inclination angles are. And I'm plotting them here as a function of this azimuthal order. So that's the number of nodes that are crossing the equator. And as you can see here, there's kind of a distribution in the stars with respect to inclination angle and what this azimuthal order is. And that turns out is something we would predict to see for solar-like stars, which is shown here on the right, where we have oscillations that are traveling in the direction or opposite direction of the rotation axis of the star. We don't really see them if we observe the star at a certain angle. Yeah. And this is related to the visibility of the oscillations and how these nodal lines are distributed on the surface. So if you're looking at a star, let's look at these ones first, the m equals 0 values, where we have none of the modes are crossing the equator. If we're observing the star edge on, equator on, then all these areas that you see here are going to end up canceling each other out. So you don't actually see a variation in the brightness of the star from the oscillations. Whereas if you're observing the polar pole on, then you see a larger amplitude for the oscillations, and we can actually find them. So that's what we see here. If we're observing the stars pole on, then we get these m equals 0 values for the period spacing patterns. And so the opposite is the case when all the nodes are crossing the equator. If we're observing the star pole on, we can't see the oscillations, versus if you're looking at the star equator on, they're very clear. So that's essentially what we're finding here as well. Now, briefly, I wanted to talk a bit more about the more massive stars. So I mentioned already, Kepler can't do the massive stars. It's not observing them at all. So what can we actually do in this case? And so our saving grace, very good news, is that we have now the TESS space telescope. So TESS is doing essentially a full sky survey and observing all stars in this field of view. So this is one TESS sector. And this is how the sectors are overlapping. So TESS is observing for 27 days at a time, and then it's shifting the sector and continuous observation. And where these sectors overlap, you get a long continuous light curves. And it does so by switching back and forth with which hemisphere that it's observing. And now we're actually getting several years of observations for the same stars as well, but with some gaps in them. And so just as an example, I'm showing here in the colored symbols, not these black ones, are just a variability study that we did for a sample of 154 O and B type stars from the first light data of the TESS Space Telescope. Now, I really want you to take away is that these stars have a lot of different types of variability that are super interesting to study, and are really opening up new opportunities with TESS for studying massive stars. Now, the ones that I'm most excited about are the opportunities to study stars, massive stars and associations and clusters. And now the difference or the similarity between the three of them is that these stars all form from the same molecular cloud. So they're expected to have similar ages and chemical composition. So that's super important when we do the asteroseismic modeling. That means that age and chemical composition is something that we can limit and not include in the modeling. So those are very important constraints to be able to include. What's the difference between these groups of stars is the number of stars that they have, their ages, and also how chemically or gravitationally bound they are. So looking at the OB associations, they have much fewer stars, but they're younger and therefore have a lot of O and B type stars in them. So those are the main ones that I'm interested in. They're also a bit easier to study than, for example, open clusters, because since they're not gravitationally bound, they're spread over a much larger part of the sky. And that's very important when we're looking at TESS data, because the pixel sizes of TESS are very large compared to, for example, Kepler. So I'm showing you an image of an open cluster, M67, taken using super stamp images with Kepler, or the repurposed Kepler mission called K2. And on the right is the same image taken from TESS. Okay, so there is a slight rotation between the two, but I think it's fairly obvious that the resolution in the TESS data is much lower than it is in the Kepler. Yeah, and that's because the TESS pixel sizes are about 5 times larger than Kepler. So that's something we have to worry about. And also, since the OB associations, the stars are spread out much further, that means that this is less of an issue compared to if you look at the open clusters instead. So the studies I'm doing now are focusing on 6 different OB associations, which have all been observed by TESS, where the memberships have recently been redetermined using data from the Gaia Space Telescope. And you see here the distribution of these stars on the sky. And in total, we have just from these 6 OB associations, 650 OB stars. Okay, so that's much bigger than the 26 stars that I looked at previously with Kepler. And just very briefly, the type of things we are looking for in these associations are pulsating stars. We see an example of that here. We have the light curve on top, variation in flux as a function of time, the corresponding Fourier transform. And on the left here, you see the position of these stars in the OB associations for which we have found oscillations, and the number of independent oscillations that were found for that given star. So there's about 340 pulsating stars that we found that we can now try and do asteroseismic modeling for. And also for the more massive stars, we found examples of cases where there is an increase in power in the power density spectrum, as we call it, towards lower frequencies. And this amplitude of the increase in power is what these data points have been color-coded by. So this is some new information that we found. These stochastic low frequency variability signals that I'm showing you here are something that have been found before in massive stars, and now we're able to expand on the sample of such known stars as well. So I hope what you'll take away from my talk is that asteroseismology is super cool. We can use it for a lot of interesting things. We can tell what the internal mixing and rotation of the stars look like. We're able to do an ensemble asteroseismic modeling for 26 SPB stars observed by Kepler, and found that the mixing levels are very diverse, but there seems to be a preference for more stratified mixing inside the stars. And finally, TESS is opening up new exciting opportunities for studying massive stars, especially in OP associations. With that, I'd like to thank you for your attention and happy to take questions.
Questions? Yes, Gary.
In the box you showed where the near core rotation was decreasing
Mhm.
the value,
Yeah.
right at the end of the models showed a very sharp uplift to higher rotation.
Mhm.
Is that physical or is that just something even more?
Yeah, so that's related to, that is physical. So it's related to how the radius is changing of the star. So that's at the very end of the main sequence evolution. There's this very fast evolution towards the left, where the star is also increasing even more in size. There's changes in the size of the star at that point.
So that's driving apparent increase in the rotation.
Yes.
You're talking about the same slide. Can you go back to the slide where you have models or tissue?
This one?
Yes, thanks.
Yeah.
So is there any evidence showing differential rotation in SPB stars?
Yeah, so the thing with the SPB stars, so these are just modeling one pattern at a time, essentially. And the SPB stars, the gravity modes, are most sensitive to what's happening near the core of the stars. So what can be done, it's better if you have multiple patterns and try to model, but also if the stars are slowly rotating, then you can really clearly see that the oscillation modes get split. And that allows you to very easily measure the rotation rate of the star without having to do this modeling of the slope, let's say. And for the stars that are slowly rotating and where we could really find these rotational splitting, so there are only really a couple of cases where that has been possible. And there what has been found, so one star was in essentially a triple system where what they found, but doing an inverse techniques of trying to model what the rotation profile of the star is, then up to about 90% of the radius, the star was rigidly rotating, but the outer percentages, there was a speed up in the rotation rate of the star. And so the authors deduce that that's because you have binary interactions that's speeding up the surface rotation of the star. There's another example of a star where these inversion techniques have been used to try to really infer what the rotation profile looks like. And that has showed that for that particular star was hinting that the surface is rotating faster than the star, but also in the opposite direction, which is interesting. But as it turns out, there are hydrodynamical simulations for internal gravity waves in stars that have shown that if the star is rotating slowly, you could get these kind of counter rotating profiles for the stars as well.
That's cool. Actually, that's one of my comments. So one way to trying to detect the differentiation in SPB stars would be using either binarity or the triple system, just a set, or the chemical spores on the surface, like hosted by mercury, manganese,
Sure.
chemical specialties. So, and then this other one would be like using hybrid stars. SPB beta 7 because we're looking at the different modes, G modes
Yes.
or P modes.
Yes. Yeah. Yes. So what we're talking about here, gravity modes, pulsations have gravity as a dominant restoring force, and they're most sensitive to the near core regions of the star. Stars can also have pressure mode oscillations, where pressure is the dominant restoring force, and those are mostly sensitive to the outer envelope of the star. So the best scenario is that if you have stars that have both types of oscillations, then you can get a direct measurement of the rotation of both the surface or the envelope of the star and also the near core rotation, and have those measurements. Unfortunately, we don't have really that many stars, or we can see both, but that's certainly something I know people are working on as well.
Mark?
So I'm trying to understand, to what extent do these models depend on making some assumption or any assumption about the initial angular momentum content of the star?
Yeah.
I mean, you're plotting everything in terms of
Yeah.
omega relative to omega
It
zams,
does,
but
yeah.
do things depend on what
Yeah.
omega zams is? Or?
Yeah, so for the green one that I'm showing here with the Sprite-Taylor dynamo, right here, I've assumed at the beginning that the star is rotating at 10% critical. What happens if you increase or decrease that is that essentially these green curves end up spanning the entire region between the orange and the blue. So the two cases of no angular momentum transport and effectively solid body rotation, which is very efficient angular momentum transport scenarios. And it's
Okay, but in those scenarios, so the orange and the blue aren't sensitive to the initial value of omega zams?
not really, no. Yeah. So what is the case though? So what we would like to be able to do. So you might see here, we only have very few stars at the CR8 main sequence. Yeah. So the ideal case would be to be able to expand the sample to really have some younger stars and get better constraints on what the initial rotation is, because I will give you more information on where in this diagram we expect the models to be at. Yeah.
Yeah, so yeah, I'm wondering how much we know about for O and B stars. I mean, when I looked at this theoretically, a decade ago, the answer was we knew nothing. Like all the models that we have for T-Tauri stars, just you try and apply them to O and B stars, they fail. So do we actually have any idea what the sort of birth angular momentum is for O and B stars?
I don't think we do at the moment. So I know studies that have been carried out is more looking at effects of the surface abundances versus the initial the rotation rate of the star and how it evolves. So because if you're looking at the mixing inside the star as coming from rotation, again, the higher amount of rotation you have, the more efficient you expect the mixing to be. And so what people have done is to try and see, okay, what's the rotation rates we need in the beginning, the initial rotation rates to get these surface abundance levels that we're observing. So those kind of studies have been done, but that's also a study in the interior mixing of the stars. And there are some examples where they're finding stars with low rotation that have enhanced nitrogen abundance. And if you're expecting to need high amount of rotation to get that, then the rotation scenario has some issues. But there are also other studies that are shown if you couple differential rotation with magnetic fields, then you can kind of pull the stars back to slowly rotating, but showing getting an enhanced nitrogen surface abundance. But specifically for initial rotation rates, I'm not aware of any studies that are available. It doesn't mean that they don't exist, but not any that I'm aware of. Yeah. Yes.
So when you're talking about the few slides before this about the diffusion coefficient for mixing, there was a factor of 10 to the 5 difference in the model fits.
Mm-hmm.
Is that actually something that you believe is real, or is it physics that's like a non-spherical star wasn't an effect?
Yes, I think the effects are. Oh, I went wrong direction. So I do think that is real, but what is true is that the models we're looking at are one-dimensional, and as soon as you move above about 70% critical, one-dimensional models, the assumptions that we're using really start to break down. So the ideal case would be able to go back and look at these stars with 2D models. The ones that we have are just not as sophisticated, let's say, than the ones we can get from the 1D models and doing evolution of that. So that's kind of what we're missing at this point, and would be great to be able to do for these stars.
let's say that low at omega critical was
Yeah.
0.1, that factor of 10 to the 5 they think is real.
In general,
Yeah.
yeah. Yeah, so it's also if you're looking at just rotational mixing inside the star. So usually they don't look directly at these diffusive mixing coefficients, they're just looking at rotation rate. But if you're looking at the actual profiles of the stars, then they do get also with rotation to this 10 to the 5, 10 to the 6, or even higher as well for those types of models.
Okay. Oh, yeah, that question.
Sorry.
Yeah.
Can I go back to the inclinations? Like
Yes.
Where you have cosine I. I was thinking about the differential rotation.
Mhm.
It's an inner
Yeah.
plot. So because you use the GMOs to measure rotation rates, right? That's for the interior of the star. And then you have cosine I, which is for the surface rotation.
Yeah.
And then this way you measure the inclination. Do you assume that there's no differentiation?
Yes, in this case, we assume solid body rotation, but you can also see there are some cases, these orange ones, where we're running into issues where we can't, the V sun I is higher than the equatorial one, so that should not really be possible. So that might be cases where we have differential rotations that are issues, or also pulsations actually also broaden the spectroscopic lines. So those give an error to the observed V sin I values as well that might change these exact values that you're measuring. So it's possible that these cases, it's because the stars are differential rotating. That could be one explanation why we can't actually do these inclination angle calculations for these stars. So there are some assumptions going in, and if they're not actually differential rotating, then doing this kind of exercise does not give you that much information. So that's true. But what we did use, again, if you look at where the stars are situated in the rotation versus age diagram, it does seem like at least the angular momentum transport is happening very efficiently and seems to be more fitting with the case of solid body rotation for this sample. Yeah, it's not that many stars in the end. It would be lovely to really populate these diagrams to get much more measurements, and maybe with TESS we can start to get there.
Okay, we will end the colloquium here today. And I'm supposed to mention that this is part of the ECR colloquium series. And as a Strommel tradition, we have a gift of a bottle of the Schmidt wine. Let's thank Mike for coming today.
Thank you.
We'll take Mike to lunch in Byton right after this, and everyone's welcome to join. We'll just meet outside in 5 minutes. All right. Thank you for coming.
Thank you.
Thank you.
Yeah.